On January 22, 2026, something extraordinary happened in our solar system. An interstellar object known as 3I Atlas reached what astronomers describe as its full moon phase. The timing was perfect. The Hubble Space Telescope was watching, and what it captured has reignited one of the most puzzling mysteries in modern astronomy. This wasn't just another comet sighting. The images revealed something that challenges our understanding of natural objects: a tail pointing toward the sun instead of away from it, along with three symmetrically arranged jets of material spaced exactly 120 degrees apart. Harvard astrophysicist Professor Avi Loeb, who has been tracking this object since its discovery, received the Hubble data just hours after the alignment. His reaction wasn't simple excitement about confirming what we know. It was concern about explaining what we're seeing. The story of 3I Atlas begins with a simple fact that most people don't realize. We can't see everything in our solar system. Objects smaller than a football field located beyond 10 times Earth's distance from the Sun are essentially invisible to our telescopes. They don't reflect enough sunlight for detection. This creates a massive blind spot in our cosmic neighborhood, particularly beyond Neptune's orbit. When astronomers discovered 3I Atlas, they immediately knew it was special. The I in its designation stands for interstellar. This object originated outside our solar system and is merely passing through. Only 3 such objects have ever been confirmed in human history. The first was Oumuamua in 2017. The second was 2I Borisov in 2019, and now 3I Atlas. Each one has taught us that interstellar visitors are far more common than we imagined. But 3I Atlas isn't behaving like its predecessors. Traditional comets follow predictable patterns established over centuries of observation. As they approach the Sun, solar radiation heats their icy surfaces, creating jets of gas and dust that stream away from our star, forming the classic comet tail we see in photographs. It's basic physics. Radiation pressure and solar wind push material outward, away from the heat source. 3I Atlas violates this fundamental principle. Instead of a tail pointing away from the Sun, it displays what Loeb calls an anti-tail, a prominent jet of material aimed directly at our star. This isn't a perspective illusion or an observational artifact. Multiple telescopes from different positions have confirmed it. The object is literally shooting material toward the Sun, defying the forces that should be pushing everything away. The January 22 observation was particularly significant because of the geometric alignment. On that date, Earth, 3I Atlas, and the Sun formed an almost perfect straight line, with the object positioned on the far side of the Sun. From our perspective, the alignment was precise to within 0.69 degrees. This configuration is astronomically rare, even for objects within our own solar system, let alone interstellar visitors on hyperbolic trajectories. For 3I Atlas specifically, it created what astronomers call opposition geometry. Similar to how we see a full moon when Earth sits between the Sun and Moon, during opposition, an object receives maximum illumination with zero shadowing. Every surface facing us also faces the Sun directly. This should have triggered a dramatic brightness surge, something called the opposition effect, where reflected light intensity increases nonlinearly. When Hubble's data came through, astronomers applied a specialized image processing technique called the Larson-Sekanina filter. This mathematical tool removes spherically symmetric glow, the diffused cloud of dust surrounding the nucleus, to reveal structural details hidden beneath. What emerged from that filtered data was unexpected. After stripping away the smooth background glow, 3 distinct jets became visible, emanating from the central nucleus. These weren't random outgassing events or chaotic eruptions. They were organized, symmetric, separated by exactly 120 degrees, perfect thirds of a circle. Each jet appeared to have similar intensity and morphology. In geometric terms, they formed a perfect trigonal pattern around the rotation axis. To understand why this matters, we need to talk about how comets actually work. Natural comets are irregularly shaped chunks of ice, rock, and frozen gases held together by gravity. Their surfaces are chaotic landscapes of craters, fractures, and compositional variations. When solar heating triggers outgassing, jets emerge from wherever volatile ices happen to be concentrated near the surface, usually from areas that receive maximum solar heating. These jets are random in distribution because the internal structure of a comet is random. You might get 2 jets or 5 or 12. They might be clustered on one hemisphere or scattered across the surface, but you almost never get perfect geometric spacing that requires either extraordinary coincidence or deliberate engineering. The 3-jet configuration of 3I Atlas resembles something very specific in aerospace engineering, a reaction control system. Modern spacecraft use symmetrically arranged thrusters to maintain attitude control and stabilization along multiple axes. If you want to control rotation in 2 dimensions while maintaining thrust along a third axis, 3 jets spaced 120 degrees apart represent an efficient design solution. Multiple engineers who specialize in spacecraft propulsion systems have independently contacted Loeb, noting this similarity. They've pointed out that historical spacecraft designs from various space programs have proposed exactly this configuration for long-duration interstellar probes. The antitail could represent the primary propulsion axis, while the 3 symmetric jets provide attitude control. Loeb's team has also determined the object's rotation period through 2 independent methods. First, by measuring periodic variations in brightness as different parts of the surface rotate in and out of view. Second, by tracking how the jet system wobbles in space, similar to how a lighthouse beam sweeps across the horizon as the tower rotates. Both methods converge on the same value, 7.1 hours. This rotation creates a gyroscopic effect, and the antitail appears to align closely with the rotation axis. When an object spins, jets emanating along the rotation axis remain stable, while jets emerging from the equator wobble with each revolution. The observations show the antitail maintaining consistent orientation, while the 3 symmetric jets precess, exactly what you'd expect if the antitail represents axial thrust and the 3 jets provide lateral control. The implications become more intriguing when we consider the object's trajectory and composition. Spectroscopic analysis has detected the emission of cyanide gas, a compound highly toxic to Earth life but also a common component in cometary ices. However, Loeb has calculated that none of this material poses any risk to Earth. The object moves at about 60 km/s relative to our solar system, and its orbital path never intersects the plane of Earth's orbit. Additionally, solar radiation pressure and solar wind push the outgassing material away from the inner solar system. We're observing this object from a safe distance, watching it release materials that will never come near our planet. But here's what makes the story even stranger. The object's velocity at 60 kilometers matches exactly the escape velocity from Jupiter's surface. This is a remarkable coincidence. Jupiter, despite being a gas giant without a solid surface in the traditional sense, has a defined escape velocity based on its enormous mass. If you could launch something from the outer layers of Jupiter's atmosphere with exactly 60 km/s of velocity, it would escape Jupiter's gravitational field entirely. The fact that 3I Atlas travels at precisely this speed raises questions about the object's origin and purpose. On March 16, 2026, those questions may get new answers. That's when 3I Atlas reaches its closest approach to Jupiter, passing within 53.5 million kilometers of the giant planet. This distance places the object exactly at what's called the Hill sphere boundary, the region where Jupiter's gravitational influence begins to dominate over the Sun's gravity. At this critical threshold, orbital mechanics become extremely sensitive to small perturbations. If 3I Atlas were to release any smaller objects at this moment, and if those objects possessed even minimal ability to adjust their velocity, they could enter stable orbits around Jupiter rather than continuing on the interstellar trajectory. This scenario isn't science fiction. It's orbital mechanics. For a natural rock to deposit satellites around Jupiter, it would need to somehow cancel out its substantial velocity relative to the planet. Natural processes can't do this. Gravitational interactions can deflect trajectories, but they can't create the precise velocity changes needed to transition from hyperbolic escape to stable orbit. That requires propulsion, the ability to intentionally change velocity by expelling mass. We have 3 spacecraft currently monitoring Jupiter or en route to the system. Juno is already there conducting detailed observations. The European Space Agency's JUICE mission and NASA's Europa Clipper are both traveling toward Jupiter and will arrive in the early 2030s. If any new objects appear in Jupiter's orbital space after March 16th, especially at the Lagrange points, gravitationally stable positions where small objects naturally accumulate, these missions will detect them. The scientific community's response to 3I Atlas has been fascinating to watch. Official statements from government space agencies have emphasized natural explanations. Meanwhile, professional astronomers have collected enormous amounts of data that remain unpublished in some cases. When 3I Atlas made its closest approach to Earth in late 2025, the James Webb Space Telescope conducted detailed observations. That data has been analyzed, but much remains under review following the standard scientific process. The delay creates an information vacuum, and vacuums get filled, often with speculation and misinformation. Loeb himself has become cautious about this aspect. He recently encountered cases where AI-generated deep-fake videos were circulating on YouTube, featuring his likeness making claims he never made. One video specifically claimed that passengers aboard 3I Atlas had sent messages to Earth saying they were disappointed in humanity and had no interest in making contact. The video looked convincing enough that some people believed it was authentic before discovering the truth. This incident prompted Loeb to create his own YouTube channel where he can post verified content directly, establishing an authenticated source that can be used to debunk fakes. The challenge of misinformation becomes even more critical when dealing with objects like 3I Atlas. The anomalies are real. The observations are documented, but explaining them requires careful analysis of complex data. And the honest answer right now is that we don't have complete information. When scientists say we're not sure yet, the public sometimes interprets that as evasion rather than intellectual honesty. When scientists offer tentative hypotheses, as Loeb does when he discusses technological possibilities, critics accuse them of sensationalism. The middle ground of genuine scientific uncertainty becomes difficult to maintain in a media environment that demands definitive answers. Looking forward beyond the March 16th Jupiter encounter, several scenarios remain possible. First, 3I Atlas could pass Jupiter uneventfully and continue on its trajectory out of the solar system. The anomalies would remain unexplained, added to a growing list of astronomical mysteries we can't yet resolve. Second, the encounter could trigger new activity, additional outgassing, fragmentation, or trajectory changes that provide new data about the object's composition and structure. Third, in the most intriguing scenario, the object could release smaller components that enter Jupiter's orbital system, definitively proving technological origin, since no natural process can accomplish that feat. What makes this situation uniquely challenging is that we're trying to identify artificial objects using the same methods we use to study natural ones. Our telescopes detect reflected sunlight. Our spectrographs measure chemical compositions. Our tracking systems plot trajectories. All of these techniques assume the object is passive, that it reflects light according to its surface properties, emits chemicals based on temperature and composition, and moves according to gravitational forces and radiation pressure. But if 3I Atlas possesses any form of active control, even something as simple as adjustable surface properties or directional outgassing, it could potentially evade definitive classification. Loeb published a paper exploring this exact problem. He calculated that an artificial light source as bright as the city of Tokyo, positioned at Pluto's distance from the Sun, would be detectable by the Hubble Space Telescope in deep imaging mode. The detection method relies on how brightness changes with distance. Natural objects reflecting sunlight grow dimmer with the fourth power of distance. They're affected both by receiving less light from the sun and being farther from our telescopes. Artificial light sources only dim with the square of distance, following the same inverse square law as any light bulb. The different rates of brightness change provide a clear signature distinguishing active light sources from passive reflectors. But here's the problem. Nobody has systematically searched for such objects. When astronomers discover trans-Neptunian objects, they automatically assume those objects reflect sunlight and don't bother checking if they might generate their own illumination. This assumption could be wrong. If a civilization established an outpost or monitoring station beyond Neptune using technology that generates visible light, and if that installation were smaller than a few kilometers in size, we wouldn't detect it unless it actively illuminated itself, and we've never looked specifically for such signals. This brings us back to the fundamental question that 3i Atlas poses. Not just what this specific object is, but what our observational blind spots might be hiding. We've become very good at detecting natural phenomena. Our telescopes, spectrographs, and detection algorithms are optimized for stars, planets, asteroids, and comets. But we're not systematically looking for artificial objects because until recently, the assumption was that any such objects would be obviously artificial. 3i Atlas challenges that assumption. If it's natural, it represents a type of comet we've never encountered before, one that violates basic principles of comet behavior through some mechanism we haven't yet identified. If it's artificial, it represents technology sophisticated enough to mimic natural phenomena while still displaying subtle anomalies that suggest purposeful design. Either possibility expands our understanding, but in fundamentally different directions. A natural explanation requires new physics or chemistry. An artificial explanation requires accepting that we're not alone and that our cosmic neighbors possess technology capable of interstellar travel. Right now, as you read this, 3i Atlas is moving through space at around 60 km/s. In the coming weeks after January 2026, it continued toward Jupiter. Ground-based telescopes are tracking it. The Juno spacecraft is preparing observation sequences. Researchers are analyzing the January 22nd data, comparing brightness measurements, studying the jet system's geometry, and building models to explain what they're seeing. The data will come out, the papers will be published, and Loeb has promised to update his assessment once that information becomes public, to state clearly based on the totality of evidence whether he believes this object is more likely natural or technological. This isn't just another space rock passing through our neighborhood. This is potentially the most important astronomical object currently under observation. If natural, it's teaching us that comets can behave in ways we never imagined. If artificial, it's the first confirmed interstellar technology humanity has ever observed. Either way, the encounter with Jupiter happened, and whatever 3i Atlas did next either deepened the mystery or provided the answers we're looking for. The data is being collected, the analysis continues, and somewhere in that data lies the truth about what's really happening in our solar system.